Hello there, Mr. Chan here, about to do a video lesson for Algebra 2, 1-6 linear systems. If you guys can turn your note takers to page 21. If you're following along in the textbook, we're on page 47. We have a little opener involving a graph. Here we go. The graph shows two lines that intersect at one point. What are the proximate coordinates of the point of intersection? That intersection right there looks about, let's go ahead and identify the x value first. It's about 3 point something, I don't know, maybe 3.2. How about the y value? That's about, I don't know, 4.7. So that would be an approximate answer to that system of two lines. Let's put that down. Okay, nice little start. Second question, how could you verify whether the coordinates you estimated are, in fact, the solution? Is the point the solution to the equations of both lines? Well, in order for it to be a solution, it has to be true for both lines. So the answer is yes. And that solution is the intersection. Okay, I'm going to skip the next question, but I'll answer the next question at the bottom. The graphs of two equations, this is separate from the problem we just started, appear to intersect at the point 2, 3. The key here, of course, the word appear. Does that guarantee that x equals 2 and y equals 3 is a solution to both equations? I'm going to say no. You might have to verify it with other ways. Now this section is actually considered a review from Algebra 1. Let's flip to the next page, page 22. All right, so from Algebra 1, when we solve systems of linear equations, write this down at the top. We used three different techniques. They included graphing, substitution, and elimination. Each one has its advantages and disadvantages, depending on how complex the problem is. We're going to jump into example 1a and try one of these techniques. Notice the equations for 1a are 2x plus y equals -1 and 5y minus 6x equals 7. It could be rearranged, meaning the x's and y's for elimination. But I think because I see y by itself right here, I'm going to try to use substitution. To do that, I want to isolate y and substitute what it equals to into the second equation. I'm going to move the 2x to the other side. To do that, I need to subtract 2x. Aha. So that is what y equals to, -1 minus 2x. I'm going to use the technique of substituting in to y in the second equation. It's going to be a little crowded here, so Please be patient. So you see a big gap there with parentheses. I'm going to put in the -1 minus 2x into that gap. I'm going to go ahead and distribute the 5 and solve for x. Remember, the whole point of using these methods is to eliminate a variable. Combine like terms on the left-hand side. And now if it's ready to be solved for x by undoing operations. Definitely running out of room here. Wish me luck here. So I have left on the left-hand side -16x equals to 12. Divide through by -16. All right, this fraction, 12 over -16, can be reduced by 4, and that'll give me -3/4. That's half the answer, half of a coordinate. I'm going to take that answer, -3/4, and substitute it back in to my isolated equation from earlier. Right there. Because I don't have a lot of room, I'm going to use the white space above that to finish it off. Here we go. Y equals -1 minus 2 times the answer I just got, -3/4. And let's clean it up. Order of operations tells me to multiply. Negative times a negative is a positive 6/4. Ouch. Complex number there. -1 plus 1.5, because that 6/4 is 1.5. So that's going to be 0.5 or a half. So yay, there's my answer. I'm going to go ahead and write that as a coordinate pair. And there's my answer. There are a lot of ways to check this answer, including graphing, but there it is. I'm going to show it to you as a graph using Desmos in a moment. All right, hang tight. We're going to switch screens here to Desmos. Now I have y equals -2x minus 1 and y equals 6/5 x plus 7/5. You might be curious as to where the second one came from. I'm going to pop back up to the first one again, the notes, and show you that the second equation needs to be isolated in order for it to work with the graphing calculator or Desmos. So let me show you the second one here, this part right there. 5y minus 6x equals 7 needs to be manipulated so you're isolating the variable y. I'll show you really quick. So the key to isolating is isolate the letter y, move the 6x over by adding 6x, and then of course dividing by 5 next. It's kind of cramped here. I apologize. Aha, when you divide by 5, you'll get the equation you saw in the Desmos screen right there. 6x over 5 plus 7/5. Okay, and the other one was y equals -1 minus 2x. I moved it in mx plus b form, so you might think it's just backwards. No, it's okay. So let me show you what happens under Desmos. I'll turn on the first equation, there it is, and I'll turn on the second equation, there it is. Hover my mouse over that and click on that point, I believe will work. There it is, negative 0.75, which is 3/4, and 0.5, which is 1/2. Great. Let's go back to our OneNote. This is one way of checking it. I'm going to draw that on my OneNote here. I'm just copying from the Desmos, so you don't see it, I do. So the first line is negative 2x minus 1. And the second one is a little bit harder to graph, 6/5 x plus 7/5. 7/5 is 1 2/5, I guess. And yeah, looks like this right there. The intersection is the answer we got through Desmos and through substitution. I'll just jot this down that we graphed it on one of our devices. Moving on to 1b, we have a system of linear equations where all the x's are lined up and all the y's are lined up and so on. Let me zoom in a little bit so you can see a bit better. Now, elimination, you recall from Algebra 1, is to get rid of a variable or a column as soon as possible. Sometimes you might have to manipulate a row with a multiple and add it or subtract it to another row. It doesn't really matter which column you choose, x's or y's. Pick the one that's the easiest. For example, if we were just to focus on the x's here, they can go away if you can make them a zero pair. 3 and 6 do go into each other. I can make the 3 into a 6 and make it negative, so that will create a zero pair. So that is my strategy. I want to make the 3 into a negative 6 by multiplying the first equation by negative 2 to everything. I'm going to multiply to here, here, and here, and rewrite it. And so we get, here we go, negative 2 times 3x is negative 6x. Negative 2 times 2y is minus 4y. And negative 2 times 5 is negative 10. I'm going to bring over the second row. And now I can go ahead and add all the columns. It'll essentially eliminate, that's what the name of this process, the first column, the x's, they go away. Now, sometimes when we use elimination or substitution, we end up with something very strange. And this problem thrown at you is been given because they kind of know, the authors, that you've been through Algebra 1 and you've seen a process of getting an answer, blah, blah, blah. But sometimes what happens is, whoa, what happens to my y's? Not only do the x's go away, the y's go away too. And if I add negative 10 to 3, I get negative 7. We end up with a strange situation where the variable disappears and we're left with a dilemma. Now recall, when we're doing elimination, substitution, or graphing of systems, we have 3 scenarios that can happen. Scenario number 1, you get an intersection of 2 lines. That's one solution. The other 2 scenarios we're about to see can also happen. What happens if they're parallel lines? Do they ever cross? No. This is where we have no solution. The third possibility is what happens if they happen to be the same line? When they're the same line, all the points coincide infinitely. When that happens, this is considered to be all real solutions or infinite number of solutions. These were all done in Algebra 1. So our situation is one of the two other scenarios, either no solution or infinite solutions. Our answer, because the variables disappear, is considered to be dun, 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 false. 0 does not equal to -7. This is a false statement. Because it's a false statement, that means there's no solutions to the system. These are parallel lines. Little side note, because we're basically done with 1B. The other situation, infinite solutions, is when you get a true statement. You know, like 7 equals 7 or 44 equals 44. If you get a true statement, that means you have infinite solutions and it is the same line. Just wanted to point that out. That has nothing to do with the example we just did on 1B. All right, that was a quick review of graphing, substitution, and elimination in one example, broken up into 3 little sub-examples. The next example involves solving a system of linear inequalities. Inequalities is where you are shading above or below the line, or you have the line as being a boundary line that is dashed or solid. Let's go through that right now. We have 4 lines, in this case, inequalities. We need to isolate the letter Y in the first 2. Let's do that. Now I notice there's a 2x. I need to move that 2x to the other side. When I move it, I'm going to have to subtract it, and that'll give me y is less than or equal to -2x plus 14. Aha! There's my first inequality. Let's take a look at our second one. I need to not only move the x, but I also need to divide by 2 eventually. So remember those 2 moves, because we're now in Algebra 2. You got to be able to mentally see that move. I'm going to move the x over, that becomes -x with the 10. And then I'm going to divide by 2 to both sides. That leaves me with the y. That 10 over 2, of course, we know is 5. And there's our second one. Now I noticed something very interesting. These 4 inequalities all happen to fall in the first quadrant. I'm going to go ahead and set my axes that way. Here's my y-axis and my x-axis. I've already color-coded them so you can see it. These lines we're about to graph are called border lines. When are they solid? Well, when your inequalities look like this. When are they dashed? When they look like this. Interesting, all of our inequalities happen to be all solid, so we'll just go with the flow there. In a moment, we'll talk about how things are shaded above or below the line. You know what? Let's do that right now. Shade. When you have less than or equal to or less than, you want to shade below the borderline. If it's greater than or equal to or greater than, you want to shade above the borderline. Okay? All right. This is something we've done in Algebra 1. Hopefully this is review, or maybe it's been so long, maybe you have a little bit of a memory of it. I don't know. Let's graph the first one. Y is less than or equal to -2x plus 14. Looks like I need to go by 2's. in order for this to work. Because my y-intercept is 14. That's crazy. So there it is. Put a point at 14. Its slope is negative 2 over 1. It's a negative slope. So let's do that. Negative 2 over 1 and so on. It's a solid line. I'm going to go ahead and draw my solid red line. Bam. The symbol is less than or equal to, which means I'm going to shade below the solid line. I have a habit of just drawing arrows to show where that will eventually go. See, we have to deal with 4 separate inequalities, and the final answer is where all 4 of those inequalities overlap. Second inequality, y is less than or equal to negative 1/2 x plus 5. Let's put it down at 5 on the y-axis for my y-intercept. The slope is negative 1 over 2. So from the y-intercept, I went down 1 over 2. It's also solid. And this one is also shaded below. Interesting. The last two are basically the x and the y-axis. X is greater than or equal to 0 is a vertical line. It's basically the y-axis, so let's draw that at as x equals 0. Because it's a vertical line, there's really no above or below. You just follow the arrow. Greater than or equal to, we're going to shade to the right of that vertical line. This is shaping up. We can see it. The red's going down, the orange is going down, the green's going to the right. You see how they're kind of overlapping maybe? Last inequality is a horizontal line. It's the x-axis, where it crosses the y-axis at 0. This time it says greater than or equal to, this is above the line. So I hope you guys can visualize this. I'm going to go ahead and shade where all 4 inequalities overlap each other, and it's in here. This quadrilateral region, which happens to have 4 endpoints, 0, 0, looks like over here 7, 0, 6, 2 maybe? Maybe. And over here 0, 5. All right, are there any questions? We're going to go ahead and move on to example 3 if there aren't any questions. Let's do that. We've done substitution, elimination, graphing, and now inequalities. Holy cow. That's like a week and a half of Algebra 1 right there. We'll skip this, habits of mind, and jump to, oh, systems of equations in 3 variables. You may use your graphing calculator or use elimination and substitution. They're giving us that option this year. I'm going to do 3A by hand off to the left here. It's going to need a lot of room. One of the mistakes that people have when they're dealing with more than 2 equations is keeping track of which variables you're trying to get rid of. Before I do that, I'm going to label this equation 1, equation 2, and equation 3. I'm going to use elimination off to the side here. And we need to focus. Let's pick a variable to get rid of, and then pick a pair of equations to help us do that. I'm looking at all the x's, they're all positive, not a good choice. I'm looking at the y's and the z's, either one of those are definitely fine. Let me pick on 2 of the equations. Let's pick on 1 and 2. I'm going to bring them over. I'm going to use equations 1 and 2. I'm going to line them up. The nice thing about these problems right here is that the y's already are opposite. They are ready to be eliminated because they are a zero pair. So the key right now is we're going to stick to getting rid of the y's. When we do our second pair of equations, you want to do the same exact thing. You do not want to pick on another variable, x's or z's. That would create confusion. So using the idea of elimination, if I add the columns, I will get 2x, the y's go away, plus 2z equals 4. Leave that alone for now. Let's go and pick on another pair of equations. I'm going to at least keep equation 2 because it's negative, and let's do equation 3. And do the same exact thing. All right. Remember, our goal is to eliminate y first. You could have picked any other letter, but y seems the easiest to do. All right, I'm going to add those columns. 2x, y's go away. The z's go away too. Bonus. Kinda. Looks like I can go further with the second pair of equations. I'm going to go and divide by 2 because we've eliminated both y's and z's. That's nice. X equals to 3/2. You know what? This is basically, I'm going to take that information and substitute into my first equation right there. I know it's a fraction. Let's keep our fingers crossed and hope this is not going to be too ugly. Plug in the 3/2. Oh, how nice. The 2's go away. As a fraction, that leaves me 3 plus 2z equals 4. Subtract 3 to both sides and divide by 2. Little glitch there. Little OCD. I wanted it to be a black pen there. Divide by 2. Z equals 1/2. Hey, not bad. Z is 1/2. X is 3/2. I can now take that answer and we need to plug it into one of the original equations. It really doesn't matter which one, to be honest with you. Let's just plug it into one of the, it doesn't matter. Let's do this. Whoa. And take my other answer, x equals 3/2, and put it right here. Whoa. And then solve that part. Gets a little messy, doesn't it? We have x plus y minus z equals 2. Okay? Those are placeholders. Did I put down x on accident? I'm sorry. Little mistake. I meant for the x to go in the other spot right there. Ha ha ha. X plus y minus z equals 2. Sometimes you want to catch yourself making errors. It happens. Even the best of them make mistakes. I know fractions are not fun, but you know what? On the left side, 3/2 minus 1/2 is 2/2, which is just 1. Nice. So that 3/2 and the minus 1/2 is 2/2, which is just 2/2, which is just 1. Go ahead and solve for y, add 1 to both sides. Y equals 3. Woo! That was not easy. We're finally done. When you get an answer, be very careful. Put it in alphabetical order, x, y's, and z's. We have 3/2, comma, 3, comma, 1/2. Now remember that answer, okay? Remember that answer. We're going to check with the Desmos app. It's kind of cool. I mean, we're always looking for work from teachers, of course. But that 3 halves, did I put a 3 there? Uh-oh, I think I made a mistake. Huh. We're going to go ahead and check, okay? Sometimes we make mistakes. Maybe there's a mistake on my notes that I posted last year. Uh-oh. So under Desmos, besides graphing, there are other tools that you can do. You can click on something called a matrix calculator. I'm going to click on new matrix, and this is going to be 3 rows by 4 columns. And I'm going to put in, these are called the leading coefficients into this matrix. We'll talk more about that in a second on the last page there. It'll be 1x plus 1y. I'm just putting in the original problem from 3a plus 1z. This is kind of cool. You can check your answers with these matrix calculators. Equals 3. Go down here. We have 1x minus y. I wonder if that work. Hope so. Plus 1. Using a mouse, it's a little antiquated. A little slow. Trying to record and talk at the same time and click. Thanks for being patient. So I'm doing something called putting in the leading coefficients of these things. And now I'm going to press enter. And there's a lot of things we can do here. We can find the RREF, that's called the reduce row echelon form of matrix A. And aha! I guess I might have been wrong. The true answer is 3 halves, 1, and 1/2. So I might have made a mistake with one of my answers here. It happens. Let's go back and see where we made a mistake under my notes. So this is the problem right there. That should be a 1. Let me check the equation that I'm using. I have x plus y minus z equals to 2. Oh, I see my mistake. 3 halves minus 1/2 is positive 1, not negative 1. This is a great teaching moment. Mr. Chan made a mistake by having the wrong sign there. Y equals 1. Psh. Yay, there it is. Now I kind of know ahead of time about 3b. Those numbers we're going to plug into a graphing calculator. In this case, I'm going to invoke Desmos again. And we're going to go ahead and clear everything and start over. And let's do a new matrix. This is called the 3x4 matrix, 3 rows by 4 columns. I'm going to put in the leading coefficients for 3b, 2x plus y minus 2z equals 3. 1x for the second row, whoops, minus 2y plus 7z equals 12. Ooh, finally, third row, 3x minus y plus 5z equals 10. enter that. I'm going to do something called reduced row echelon form of matrix A there. And look at that. You guys see this funny last row right there? 0, 0, 0, 1. The first column represents the x's, the second column represents the y's, the third column represents the z's, and the last column represents the answer that x, y, and z equals, and they can't finish it. Look at the bottom row. We have 0, 0, 0. That means all the variables disappear. That means, in this particular case, there is no solution. So that happens once in a while. So here, under a graphing calculator, or in this case, Desmos' matrix calculator, the graphing calculator gives us an error, which means there is no solution. All right, let's move to the last example of the day. That's what's required of us. The rest of the items are not required for this course. Let's jump to example 4. Now, matrix algebra is a whole separate thing in algebra that we do all kinds of stuff with. This last example is actually very easy. We're just trying to convert from one form to the other. What we have on the left in 4a is called system of equations. And actually kind of showed you that already under the Desmos calculator. Systems of equations is just a bunch of equations with x's and y's. And they usually lined up with x's and y's in each column. The other form is called a system of equations for the matrix, or matrix equations. This whole thing is called the augmented matrix. Write that down. The augmented matrix is made of two things. The first half before the vertical line is called the coefficient matrix. Because those are the coefficients of the leading, of each of the variables, x's and y's and z's. And the last one is called the constant matrix. Those are the numbers that don't change. Okay? The actual dimensions of the coefficient matrix is called the 3 by 3. And the other one is a 3 by 1. Those are rows and columns. And that's called the dimension. And technically, if I wanted to convert the augmented matrix back into a system of equations, it would look like this. 0x, you don't have to write that, plus 2y plus 3z equals 4, 8x minus 1y minus 2z equals 5, and finally 2x plus 0y plus 1z equals 9. That's it. That was pretty easy. I guess I forgot to do it with the other one, 4a. Kind of got excited about the augmented matrix. Let's finish 4a. Silly me. There we go. We'll write the bracket, vertical line, close bracket. Jot down make sure all the variables are lined up, x's and y's. Sometimes they mix it up. I'm writing the leading coefficients. And then now the constant matrices. All right. Well, that's it for me. I hope you learned something. Good luck. Thank you very much. Have a good day.